this section of 4.4 exponential and logarithmic equations in Algebra 3 is starting to wrap up the last of this unit. The whole purpose behind looking at expanding and condensing logarithms was so that you were able to solve equations. And they're not hard to solve, but it's something new for most of you, and it takes a little bit of time. So I've broken it down into, there are 2 different techniques, and each technique has 4 steps. And if you follow these steps and you just go slowly, you should be okay. So the first property that we're going to look at is called a one-to-one property. I really should have typed this with dashes in there. And the concept is very easy. If b, the exponent, b to the m power, is equal to the exponential function b to the n power, then m has to equal n. Seems simple enough. So the steps I want to leave there so you can see as I do these. For the first problem, there really isn't any work. This is 3 to the x equals 3 to the 4. When I'm solving the equation, I'm trying to find the value of x. Well, this is really just the one-to-one property. The bases are the same, so the exponents have to be the same. So all I do is say, well, x equals 4. And it's solved. The next one is going to have some more work to it. The first step in these is to rewrite so the exponents have the same base. Well, the first example, they had the same base. They had a 3. So it was easy. The second example I have a 4 and an 8. They don't have the same base. But the better number sense you have, the easier this becomes. And I usually show this by looking at the 4 and the 8 and thinking, well, I can make them both a base of 2. If I'm thinking exponential functions, I know that 4 is equal to 2 squared. So I can change this 4 to the x plus c, and I can say, well, this is 2 squared raised to the x plus 3. Well, I can make the 8 into a base of 4 also. I know that 8 is equal to 2 cubed. And that's what I mean about a good number sense. And we're going to use a lot of these numbers over and over again. So I'm going to say 8, I'm going to replace 8 with 2 cubed and raise that to the 5x power. And I would start to recognize bases of 8. So I know 16 is 2 to the 4th. 32 is 2 to the 5th. 64 is 2 to the 6th. And those are numbers that I might need to use later on. So then I'm going to use the product, or the property of exponents. When I raise to a power, I'm going to multiply. So this base of 2 stays 2. But then I'm going to multiply the 2 and the x plus 3. So it's going to give me 2x plus 6. On the other side of the equation, I'm going to multiply the 3 and the 5x. So I get 2 to the 15x. So now I did satisfy the first step. I rewrote the exponents so they have the same base. They have the base of 2. Now I want to write the exponents equal to each other. So I set 2x plus 6 equal to 15x. Next step is to solve for the variable. So I'm going to subtract 2x from both sides. I get 6 is equal to 13x. Divide by 13, I get x is equal to 6 divided by 13. And to check the solution, I want you to use the calculator. And there's many ways to do it. This is the one way I'm going to show you. I like storing a value. Try to get this glare off of it. So I'm going to take this value 6. Oops. That's not what I want. 6 divided by 13, and I'm going to store it for x. and hit enter. So now whenever I hit the value of x, it's 6/13. So I'm going to first look at the left-hand side of this equal sign. I have 4 raised to the x plus 3 power. So 4 raised to the x plus 3, and I get 121.35. Right now I don't care what I get. If it's equal to the other side, that's what I'm looking for. So the other side of the equation have 8 to the 5x power. So I type in 8 to the 5x, and I have the same value, so I know I solved it correctly. In these problems, it's not like I could ever just look at it and say, oh yeah, that's the answer. Some of them you can, but a lot of them you cannot. The next example, my bases are 1 over 25 and 125. Well, I think of the 25s, and I think, okay, well, 25 has got to be a base of 5. And I see this 25, and I know that 25 is 5 squared. But that's not what I want. I know that 5 is 5 to the first. And then if I think of it differently, I could think of 5 to the 0 is 1. 5 to the negative 1 is 1 over 5. Now I think I'm getting close. I'm getting in the right direction. 5 to the negative 2 is 1 over 25. So I'm going to change this 1 over 25 to 5 to the negative 2 power. And then I have 125, so let's see what happens. 125 is 5 cubed. So I'm going to change this 125 to 5 cubed, but I'm going to raise it to 2x plus 7 power. Now I have the bases the same, but I have to apply the property here where I'm going to multiply 3 and the 2x plus 7. And make sure you distribute. This 3 has got to be multiplied by the whole binomial, so 6x plus 21. Now that my bases are the same, I'm going to write the exponents equal to each other. So I'm going to have negative 2 equals 6x plus 21. I'm going to subtract 21, I get negative 23 equals 6x. Divide by 6, I get x is equal to negative 23 over 6. And I never put a box around it until I've checked my work. So now I'm going to do a fraction. I want negative 23 divided by 6. I'm going to store that for x. Oops. Store it for x. And then I want this 1 over 25 Now it gives me 1 over 25. That's okay. If I want a decimal, I could turn it back into a decimal, but I might not need to. Then I'm going to take 125 raised to the 2x plus 7. It says 0.04. Well, I want to see if those are the same. So I'm just going to take that 0.04, turn it back into a fraction. And that's the correct answer. So that's when I put a box around it. The other properties that I'm going to use are what's called the inverse property. The one-to-one property will not work every time. It only works if you can get the same base. So if it doesn't, if you cannot make the same base, you need to use what is called this inverse property. Basically, what you're going to do is you're going to rewrite the exponent as a logarithm. So my first example, 4 to the x equals 19. Well, here I have a 4 like I had a 4 up top, but the 19, there's no way I can rewrite the 19 to a base of 4. So that's why I need to use the inverse property. First step is to isolate the exponential term. What I mean by that is this exponent doesn't have anything multiplied by it or added to it. So that step is already done. The second step is to rewrite the exponent as a logarithm. So that means I'm going to have log base 4 of 19 equals x. Well, now that's easy. I just typed that in my calculator. So I'm going to say x is approximately equal to, because this is going to be a decimal, I do alpha window, do number 5. So log base 4 of 19. And I hit enter. This is a decimal, cannot be turned back into a fraction. And the common rule for logarithms and exponential functions is we're going to round to 3 decimal place. So the nearest thousands. So the first tens is 1, hundreds is 2, thousands is 3, but the next digit's a 9. So I'm going to make that a 4. So the answer will be 2.124. And I can check this with a calculator, but I don't want to store the rounded value. I just, right here, I'm going to store this for x. I don't round it and store for x. I want to store that whole thing. So then my equation is 4 to the x equals 19. So 4 raised to the x power is 19. So I'm good. The second example, 3 to the 2x minus 5 plus 7 equals 15. So I need to isolate the exponential term. I've got to work and get the 7 away from this exponential term. So I'm going to go ahead and subtract 7. So I have 3 to the 2x minus 5 equals 8. My base is a 3, and I have an 8 over here. I cannot use the one-to-one property. I have to use the inverse property. So I'm going to rewrite the exponent as a logarithm. So I have log base 3 of 8 equals 2x minus 5. This log base 3 of 8 is just a decimal, but I'm not going to pick up my calculator till the very end. So the first thing I'm going to do is I'm going to add 5. So I have log base 3 of 8. I want to add 5 to that. I'm putting parentheses around it just to make it easier for me to look at. Then I'm going to divide by 2. So I get x is equal to log base 3 of 8 plus 5 all divided by 2. I can then type that in my calculator. So I have got, put my fraction up. I want a log base, so I do that. Oops, 3 of 8 plus 5, and I divide it by 2. 3.446. So I'm going to put that here. And I'm going to check that answer to make sure. I didn't write that very neat. So right from here, I'm going to store that value. And then my original equation, I'm going to type 3 raised to the 2x minus 5 plus 7. It equals 15, so I did it right. Okay, then I've got one more example. I have 2 multiplied by 10 to the 3x equals 15. So to isolate the exponential term, this 2 is being multiplied by it. I can't distribute that in that. It just doesn't work with exponents. I have to divide by 2. So I get 10 to the 3x equals 15 divided by 2. Now I've got my term is isolated. I don't have anything else being multiplied or added or subtracted to the 10. So I'm going to write log base 10, I don't have to write the 10, of 15 halves equals 3x. And I could, at this point, just type my calculator. This is another way to do it. Log 15 over 2. And I don't need to put it into a fraction. It just makes it look a little bit neater. And that's equal to 3x. And I'm not rounding this there, I'm just leaving that there, and then I'm going to divide by 3. So I get x is equal to 2.9, or not 2.9, 0.29. And then instead of this, the 1, I'm going to write a 2. And then I'm going to check that, so store for x, 2, and then 10 raised to the 3x. And be careful where you put your parentheses. And that equals 15. So I've gotten that correct. And I really should say this is approximately equal to. That's what the 2 squiggly lines mean. So that's solving exponential equations. I'm going to do a different video for logarithmic equations.